Welcome, dear students, to this one more lecture on liquid drop model and its valediction. Today, we are going to be discussing in detail about spontaneous fission. Here you can see a nucleus which is split into two, and there is a process which is involved. It does not directly get split into two in one stroke. There are various stages after which it splits into two parts, and then you can see here the neutrons are just pictorially shown. Neutrons are also emitted in the process, and finally it undergoes various beta and gamma decays to reach the stable state. So this could be the, let's say, shown here pictorially, the stable state which is arrived from the parent. So that's how it this, and we're talking about here, you can consider up to this. So you can see the two genes here from the parent, and we have discussed this in the previous lecture, and we saw that one uranium-238 nucleus is split. It emits about 214 MeV of energy, and the liquid drop model was very close in predicting the value closer to 214 MeV. We had seen that last time. This is the equation which we had discussed. This is the equation for Q. If spontaneous fission has to occur, then we have seen that spontaneous fission has to occur, then this term has to be greater than this, and from that we arrived at a value z square upon E is greater than or equal to 15. Any nuclei which satisfies this condition is a candidate for spontaneous fission. That's what we have seen. Now we'll take the discussion further. We are now going to be discussing about why does the spontaneous fission not occur in nature. Otherwise, if spontaneous fission were to occur, then we would have found explosion somewhere in some part of the world on its own. In our lifetime, we haven't seen that. It must have happened earlier, or it might happen in future. But why does it? What stops the nucleus from undergoing spontaneous fission? That's what we have seen. Now, today's discussion will be based on this particular topic as to what is it that stops the nucleus from undergoing spontaneous fission, and which candidates are a good candidate for spontaneous fission to take place, or if spontaneous fission is not happening, then artificial fission candidates, who are the good candidates for artificial fission to take place. So these are some of the questions which we will be discussing today. Now this is a very important graph, and this actually sums up the entire discussion. If you understand this, then the argument will be well understood. Now we are proceeding on similar lines as we did for alpha decay. The only difference here is instead of the alpha particle tunneling out of the barrier, it is the fission fragments which are trying to tunnel out and then break into two parts, break the parent into two parts. So the process, the argument is proceeded along similar lines. We presume that in an alpha decay, the alpha particle is formed before it actually tries to tunnel out. It puts in a lot of effort. Probability of tunneling and number of effort together determines how successful the alpha particle would be in tunneling through the parent nucleus. Now, here there is one signature which is obtained. Now, if the two fission fragments are formed, now let me first explain the graph. Now we are considering this is a parent. Right now, for all simplicity, we are considering symmetric fission. Symmetric means the two halves are equal. So, okay, as I said, the argument is not going to be different if the two halves are not going to be same. Okay, so we are talking about these two fission fragments obtained from the parent. Now let's try to understand the potential experienced by the fission fragments. In order to do that, we do the similar exercise as we did for the alpha decay, and what we do is we take them separate far apart, calculate the Coulomb potential, point a graph, plot a graph, plot a point. Now this is the expression 1 upon 4 pi epsilon 0 multiplied by the product of the charge divided by r. R is the distance here, and both products are having charge ZE by 2. Z is the charge of the parent. Since it's going to be divided into 2, it's going to be Z by E by 2. So if we square it, then this becomes Z square, E square, and this becomes 2 square. So this is the expression. Then we bring them still together. Right now they are far off. Calculate the potential. This is an hypothetical situation. We wanted to trace the graph. We bring them still closer. We plot another point. Like that, we consider the two fission fragments to be absolutely coming at various distances closer to each other. Using the Coulomb potential expression, we calculate the value of the potential, because right now the attractive potential has not come into the play. It's only the Coulomb repulsive potential which we are calculating. So this is how the graph is plotted patiently, and then there is a point where the two of them they actually are side by side. So this is one fission fragment, this is another fission fragment. They are in close contact. Now when they are in close contact, this is a point at which the Coulomb potential at this point is existing. At the same time, the attractive potential also has started to come into the play. So finally, between the two, there is one point where there is a maximum value of EC. I can say the maximum value of EC, because the moment the attractive potential comes into the play, the value of EC is going to decrease. That's how you can see that the graph is decreasing. This part we are just trying to presume that it is of this shape. Of course, we are just a guess, but obviously it's going to be on a decreasing side. Now the idea is that they are in close contact like that, and then they fuse to form the original nucleus. Now if you can look at it in the other way also. Now this nucleus, let's say the two fission fragments are already formed beforehand. Okay, we're talking about spontaneous, so it's not something which is triggering it. They're already formed. Then obviously the Q which is released is of the order of, which is calculated somewhere around 200 MeV or something like that. I'm just giving you a rough figure. Okay, right now what's going to happen is this is not able to tunnel out. This is not able to tunnel out the barrier, for the simple reason that the barrier height is going to be, if this is the value of Q, if this is Q, then this barrier height is existing. If this barrier height was not there, some barrier height was not there, the particle would have tunneled out. But the very fact that the fission fragments which are presumably existing and inside the potential well and they are trying to tunnel out are not able to do that because there is some potential barrier. Now let's try to find out what could be the height of the potential barrier. One of the things which you must have heard is uranium-238. You are all quite familiar. And there is another isotope which is uranium-235 of uranium element. Now there is something called photofission. Photofission means you bombard gamma rays on the nucleus and trigger a fission artificially. Now what has been found that in uranium-235 you just need about 1 MeV energy of gamma rays to be incident for fission to occur, which means if you supply 1 MeV, then the fission fragments are able to overcome the barrier, which means the barrier height must be 1 MeV. This is a conclusion from the photofission experiment. While in the case of uranium-238, you need about 6 MeV energy of gamma rays intensity for fission to occur. And that's also one of the reasons why that you must have seen enrichment of uranium. Enrichment of uranium is nothing but conversion of uranium 238 235. So 235 is a very good candidate for fission. 238 is not a good candidate for the simple reason that the potential barrier in case of the uranium 238 is higher than 235 for the fission fragments to tunnel out of the barrier. So now here this is very very clear that if Q is whatever be the Q, right now we are talking about 200 or 210 or whatever it is, 210, 214 we had calculated, but definitely it's not going to be 214 here, the barrier height, because as the Coulomb potential at this point, the Coulomb potential and attractive potential, both of them when they are there, the potential height is going to be less than 214 MeV, which we had calculated, and the calculation which we did, and for 6 MeV for uranium 238 and 1 MeV for 235, which means this barrier height means the value of the Q, the disintegration energy for symmetric fission, and this difference, that is the peak potential barrier, this difference is greater than 0. If it is less than 0, then there is no barrier and the particle can tunnel through, the fission fragments can tunnel through, and it can spontaneously undergo fission. It will not exist in nature. So that element will not exist in nature. So that's why there is a limit in nature. You do not have very heavy elements. Even if those elements were formed, it would have undergone spontaneous fission, for which this gap, the potential barrier and the Q value is less than 0. So obviously the fission fragments are able to tunnel through. The very fact that this difference is greater than 0, and this greater than 0, I am using the word because this greater than 0 is dependent on the nucleus. For example, 238, the height, the barrier height is different. 235 it is different. Thorium it would be different. Radium it would be different. So if you take different elements, then you have different difference between the peak potential and the value of Q. So this is what is happening. So the particle is inhibited, or particle is stopped from tunneling through because of the potential barrier which is existing, and a similar potential barrier stopped the alpha particle from decaying. But in case of alpha decay, what was happening is the potential barrier height was, I think, if I remember, it was 140 MeV or so, and the alpha particle energy was 4 MeV. So it was able to tunnel out, despite having the low energy, it was able to tunnel out. But here, these fission fragments are not able to tunnel out, despite the energy difference being so less between the peak potential. The reason is simple, because they are very heavy. You know that the probability of potential of tunneling is going to be dependent on mass. Alpha particle mass is very less, here the fission fragments mass is very heavy, so that probability is also not happening despite low difference between the Coulomb potential and the potential height, potential barrier, and the value of Q. So this is the reason. Now let me come back to this original argument. Dear students, here I said they're all fissionable candidates. They can undergo spontaneous fission, but they don't undergo spontaneous fission for the reason that there's a barrier which stops them. Now for all other candidates which are less than 15, there is no chance of fission fragments at all. Even if there is a barrier or no barrier, the Q is going to be less than 0, so the fission is not going to happen. Now these guys are going to be fissionable. All those elements which satisfy this condition, they're all going to be undergoing spontaneous fission. But they don't undergo spontaneous fission very soon. It might take a very long time. The probability is going to be very less. but the probability is not 0. Now, if at all you want the fission to occur in such elements, then you have to supply energy to these elements. The energy should be such that it should be able to overcome the potential barrier so that the fission can take place. Now, the whole point is, what are we discussing here in terms of liquid drop model? In terms of liquid drop model, let us try to see, first of all, we'll calculate what is the height of the maximum Coulomb potential, and then try to see which is the condition for which the particle will immediately undergo spontaneous fission, and which is the condition for which the particles will not immediately undergo spontaneous fission but will take a finite lifetime, will have a finite lifetime, but they are a candidate for spontaneous fission. So let that calculation is what we are going to be doing next. Okay, now what we do is we again start with this expression only. Okay, this is the Coulomb potential at some distance r between the fission fragments. Now at r is equal to 2r, at r is equal to 2r means this point here, this point, what happens is at r is equal to 2r, I just put, instead of r I put 2r. You can see that instead of r I have put 2r, nothing else. Now r, you know, is nothing but r in r0, a raised to a by 3. So instead of r I am writing r0. Now a is not a, but a is a by 2. So that is to be very clearly understood. Here we have written r is equal to 2r because this is one nucleus, this is in close contact with another nucleus. Now this is r, this is r. If this is r, obviously this is also symmetric fission, so this is also r. So the distance between the two nucleus center is 2r. So that's why we written 2r here. Now r is equal to, r is actually the radius of one fission fragment. So it's going to be a by 2, r0, a raised to 1 by 3 into 2 raised to 1 by 3. Okay, so you will have to write it this way. Okay. Because if you still follow, you will understand, I hope. A is equal to r0. If this is r0, I have to write this as, this is a general expression, but in our case, this becomes a by 2 raised to 1 by 3. Okay. General expression for any radius is r is equal to r0, a raised to 1 by 3. But a in our case is not, is fission fragment. So fission fragment means a in our case is actually a by 2. That's what I wanted to specify. So I put that value here. Now I am doing some rearrangement. 2 raised to 1 by 3, 4 pi epsilon 0 multiplied by e square to r0, a raised to 1 by 3, z by 2 square. Again I am simplifying. 2 raised to 1 by 3 is here, 4 pi epsilon 0 is there, e square is there, z square is there. Now this 2 square is 4, 4 into 2 becomes 8. 8 is here, r0, a raised to 1 by 3. Now this is the value of the Coulomb coefficient. Please refer my previous presentation, initial 1 or 2 lectures of liquid drop model. So we have calculated this Coulomb coefficient. This Coulomb coefficient is equal to 1 upon 4 pi epsilon 0, 3 by 5 e square upon r0. So AC would be equal to, okay, the same thing I'm repeating here. So I am actually trying to calculate the value of e square upon r0 in terms of AC, because here I have a term. See, here I have a term. I'm trying to simplify this expression, doing nothing else. I have this term e square upon r0. So I'm trying to calculate the value in terms of Coulomb coefficient, because I know the value of Coulomb coefficient. So e square upon r0, this becomes 5 by 3, 4 pi epsilon 0 into AC. This becomes that. So I put this value back into the expression of EC. So I get 2 raised to 1 by 3, 4 pi epsilon 0, z square, 8 epsilon. Instead of e square upon r0, I write 5 by 3, 4 pi epsilon 0 AC. So this 4 pi epsilon 0, 4 pi epsilon 0 will get cancelled. 2 raised to 1 by 3 like this, 8, okay, z square upon a raised to 1 by 3 multiplied by 5 by 3 to AC. Okay, this is how finally I get. Now this can be further simplified. Okay, this can be further simplified, and if you calculate 2 raised to 1 by 3 divided by 8 into 3 and all those terms, and finally what's going to happen is, yeah, as I said, this 4 pi epsilon 0 gets cancelled here. So you're left with this terms, and if you calculate this, this turns out to be 0.262. You can use your calculator and check that. AC into this. So finally, this is turning out to be 210 MeV approximately. That is the Coulomb barrier. So that is the Coulomb barrier. If you put the value here, you put the values of Z, ZA and coefficient constant, you will get 210. So the whole idea is that this height, this barrier height, maximum barrier height, maximum Coulomb potential, I am talking about the maximum Coulomb potential, is 214 approximately, because we have taken as a slight approximation. This is actually 214. This is for the uranium 238. Okay, and the Q which you are calculating is going to be slightly less than this. This is the difference between this Q and this. And pay attention, we have taken the earlier calculation which we made of this thing. So there is going to be a difference between this barrier height and this. These are all approximate figures, so these values could be slightly more or less, but in short there is a gap, potential gap between the value of Q and this is 214. Mind you, the value of 214 which we got, okay, was this thing, and we have calculated this from here. So this is 210, sorry, I made a mistake here. Now you will ask me why it is not 214, because the attractive potential is also coming into play here. Okay. So this turns out to be 210 something. Okay, and the value of the Q which would turn out to be inside would be slightly less than that, and the nucleus will be unstable, as I said, only if your Q is going to be greater than or equal to AC. If this is surpassing the barrier, then obviously it can tunnel out. If it is not able to overcome the barrier, it will not be succeeding in tunneling out. It has to put in a lot of effort, and then there is a probability of tunneling. And from liquid drop model, we have derived this expression of Q. I think the first slide itself I have given you this value. This is the value of Q which I have taken. Okay, so that Q I use here, and EC expression I have. This is the expression for EC. So I solve this equation. I solve this equation here. This is your Q and this is your EC. From this I arrive at a condition, and all nuclei which satisfy above condition shall be unstable against spontaneous fission, which means they will immediately undergo spontaneous fission. So that's why these heavy elements, any heavy elements which are great, which is satisfying this condition, will not be existing in nature, because they would have undergone spontaneous fission. So anything which is less than this are stable against spontaneous fission, and amongst them those candidates which are Z square upon A is satisfying this condition are a candidate for spontaneous fission. I said they are candidate, but it will not happen immediately. It will take a finite probability or a finite lifetime for that to happen. Okay, so this is what we have discussed here. Now these are all the figures which we have done is just an approximate figures, but liquid drop model, the whole idea is now we have to verify this particular statement. Actually, this is liquid drop model's prediction. In nature, what is observed is Z square upon A greater than or equal to 44 don't exist in nature. So just imagine the liquid drop model is very, very close to this figure. We've just done approximate calculation, and 53 is what the liquid drop model is predicting, and in nature it is found that we don't have elements whose z square upon a is greater than or equal to 44 because they are unstable against spontaneous fission. So now let me quickly sum up right from the first slide. These are the candidates for spontaneous fission, but why don't we see them happening immediately? Why don't they undergo spontaneous fission? Is there is a gap which is existing between the peak potential barrier and the value of the Q. Q is basically, the Q means the the Q is for a fission to happen. The nucleus is broken into two parts, and the energy is released. So that Q and this peak, there is some gap. And that gap is actually inhibiting or stopping the fission fragments to tunnel out. That's the point we have discussed. And this gap is actually different for different nucleus. I mentioned for 235 it is just 1 MeV. For 238 this gap is 6 MeV. So theoretically it's very difficult to calculate the gap. We are just trying to do an estimate. So that estimate we found out, then we are trying to find out what is the peak Coulomb potential which the two nucleuses, fission fragments are experiencing. So the two is experiencing a 210, but you know that this is peak is going to be less than 210 for the simple reason that moment they come very close, then the nuclear forces come into the play, so the value is going to be lower than that, so lower than 210. This is just a presumption here. This value, where is that value? Okay, this value is just presuming that there is no nuclear forces, attractive forces coming into the play when both of them are in close contact, like that. This is just a rough calculation we are trying to do, that when they are both of them are in close contact and we presume that there is no attractive force, then what could be the maximum EC value? EC, this is the maximum. Of course, in reality, this is found to be lower than 210. It is just above the value of Q, just above the value of Q for that particular nucleus. So that is what we are doing. And then for a nucleus to be unstable, you have this condition, and from this we arrive a stability condition of 53, and as I said, which is very close to the one which is found in nature. So dear students, this is one more triumph of liquid drop model. Let me again go back. It explains successfully the most stable isobar member. Then we saw that for a fission of a fission of a uranium 238, then how much would be the binding energy? Roughly we calculated that, and we found that if it is a symmetric fission, then it would be around 210 or 14. But you know that in nature it's not symmetric fission, it's asymmetric fission, so that value is going to be little different for one nucleus to be broken into two parts. And then we found out what is the condition for spontaneous fission. So any element whose z square upon a is greater than or equal to 15 is a candidate for spontaneous fission. And then the next question we answered is, why don't we find them undergoing spontaneous fission? There is a Coulomb potential, there is a potential barrier which actually stops the fission fragments from tunneling out. And finally you arrived at a value which gives you the condition for stability against spontaneous fission. Thank you.